Hi everyone, welcome back. We're now going to get into Hamilton paths and cycles, often referred to as Hamiltonian paths and cycles. And these are after mathematician William Hamilton, who invented a game, or more of a puzzle, in which the object is to find a cycle along the edges of a dodecahedron so that the cycle contains every vertex. Here's an image of the actual game. Consists of a wooden board, and then there's wooden pegs you can place in the spots of the vertices, and the idea is you place those pegs as you visit the vertices, and you're traveling along a cycle when you're visiting these vertices, and you want to make sure you visit every vertex. So we can do this in terms of our diagram on the right. We've got the underlying game board there, and our goal is to try to find a cycle that passes through every vertex in the graph exactly once. So we could maybe start at that vertex, travel along an edge to this vertex, go to this vertex, and so on. And the idea is to travel around the graph on a cycle and visit every vertex exactly once. So pause the video and give it a shot. See if you can do it. All right, I'm assuming you paused the video and gave it a try. Let's see if we can do this. So we'll go along that edge to here. What I'm going to try to do is just try to go along the outside as far as I can. Now I'm going to go inside and visit some of the vertices. And I'm just trying to stay to the boundary, the outermost vertices, as much as I can until I have to pop in. And now I'll pop in, go around, and then back out. And it looks like we're good. We've made it. And there we go. So there is a cycle through all the vertices of the graph. This is known as a Hamilton cycle. And so that gives our definition for today. Let G be a graph. If we have a path that contains every vertex in the graph, that's called a Hamilton path or a Hamiltonian path. If we have a cycle that contains every vertex of the graph, that's what we call a Hamilton cycle or a Hamiltonian cycle. You'll see I'm interchanging between Hamilton and Hamiltonian. That's fine. You can use whichever term you want, and I'll actually use both. They mean the same thing. So let's look at some examples. So we'll start with a graph. This one has 5 vertices. And here's our edges. Does it have a Hamilton path? Let's see if we can find one. So we'll start at this vertex. I'll go along an edge, this edge, and this edge. And there we go. We found a Hamilton path. So this graph has a Hamilton path. How about a Hamilton cycle? Can we find a Hamilton cycle in that same graph? Whenever I've got a diagram drawn and we're asking, is it possible to find a Hamilton path or a Hamilton cycle? Take a moment, pause the video, see if you can find one yourself before we continue on. All right, I'm assuming you've made an attempt at finding a Hamilton cycle. And in this case, we certainly do have one. We can just go around the outside of the graph. And there we go. There is a Hamilton cycle. Let's try another graph. We'll start with a rectangle, and then we will put an edge or a vertex right in the middle with a couple edges connecting to it. Does this have a Hamilton path? And the answer is yeah, we could go like this, just zigzag through the graph, visiting all of the vertices. So this has a Hamilton path. Does it have a Hamilton cycle? So we'll redraw it here, pause the video, see if you can find a Hamilton cycle. All right, so assuming you've taken a shot at getting a Hamilton cycle and most likely weren't successful, and there's a reason for that. This does not have a Hamilton cycle. There's just no Hamilton cycle in there. And of course, if I'm going to make a statement like that, it can't just be because, well, I tried, couldn't find one. We have to be a little bit more precise than that, because maybe I just didn't try hard enough. Maybe I just wasn't creative enough in trying to link together these vertices along the edges and getting a cycle. So why can we definitively say that no matter how clever you are, there will just not be a Hamilton cycle in this graph? So why? Why is this the case? Well, let's think about maybe what happens to vertices of degree 2. This is a pretty common thing to look for in graphs when you're interested in the question of Hamilton paths and cycles. Why is that? Well, when I look at a vertex of degree 2, I know my cycle or path will have to contain that. So if it's a cycle, I know that I have to come to that vertex along one edge and then leave it along another edge. So I have to use both the edges that are incident with that vertex. So we have here a Hamilton cycle must use the, and then I'll fill in the rest. There's some number there, edges. How many edges must I use? Well, it must use that edge. 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 Why must it use those two? Because there's a vertex of degree 2 there. And so if the cycle is going to contain it, it must use one of the edges to come into it and the other one to leave it. It also must use this edge because this vertex is of degree 2. And it must use this edge. So it has to use 6 edges. So how can a cycle that contains 5 vertices use 6 edges? Well, it can't. That's impossible. A cycle on 5 vertices uses 5 edges. So this is impossible. There's just too many edges that my cycle is going to have to use. So that's how we can show that there is no Hamilton cycle. No matter how clever we are, we just can't find one because it would have had to use all of these edges. In fact, it had to use all the edges in the graph. And that was because, again, let me reiterate this, the key idea was these degree 2 vertices. It had to use the edges that were incident with those degree 2 vertices. All right, so in general, how can we go ahead and find if there is a Hamilton cycle or Hamilton path in a graph? Well, one option might be just to do an exhaustive search. If I'm interested in finding a Hamilton cycle, maybe I'll exhaustively search through all cycles and see which ones visit all the vertices. Now, of course, there's an issue with this. It's really a cost issue. So let's imagine doing the original problem, the one that Hamilton posed for the dodecahedron graph. And since we're going to find a cycle, or hope to find a cycle, I'll just pick any vertex to start with. Namely, I'll start with that top one. So let's look at all cycles that start at that vertex. So how many choices do I have for the first vertex? Just one, because I'm telling you to use that top one. How about vertex number 2? How many choices do we have? Well, there are 3 edges that I can take away from that starting vertex. So there are 3 choices for the next vertex. Once I've picked that vertex, how many choices are there from that point forward? Well, a key observation for this graph is that every vertex, no matter which one I look at, has degree 3. So this is what we call a 3 regular graph. 3 regular. All vertices have degree 3. Okay, so how can we use that? Well, once we've picked the second vertex, now we want to pick the third vertex. How many choices are there for the third vertex? Well, I came into the second vertex along one edge, and I've only got 2 choices to leave it by. So there's 2 choices to move on for there. And then for the fourth vertex, again, it's 2. And sort of worst case scenario, we end up with all the way down to the 20th vertex. Basically get 2 choices for each of these. So we are roughly on around the order of 3 times 2 to the 18 possible choices for the ordering of our vertices in creating a cycle. So we have roughly this many cycles or approximately, it's a little less than a million, so a little less than 10 to the 6 possible cycles. And those would be what we would have to check. Okay, so a million cycles, or a little less than a million cycles, not so bad in this case. But as a general method, this can get costly very fast. So here's an example of a graph, still 3 regular. It's got 70 vertices. How many cycles would we have to check to see if they are Hamilton cycles? Well, we are roughly checking the same as before, 3 times 2 to the 70 minus 2, or 68. And this is a huge number, too much for us to actually check. And we see in general that as we change the graph, add more vertices, the number of cycles to check is growing exponentially. So this is exponential. So an exhaustive approach is not going to be of much help for us. There's just too many things to check. So how are we going to decide whether a graph has a Hamilton path or a Hamilton cycle? Is it the same as we had with Euler circuits and Euler trails, in that maybe we have a criteria? If we just check that a criteria is satisfied, then we are guaranteed the existence of such a cycle. So for Euler circuits, we had that if it wasn't the singleton graph, then every vertex being of degree 2 and the graph being connected was enough to guarantee that there was an Euler circuit. Do we have the same thing in this case? Well, unfortunately, no. What this slide, I'll just go through it rather briefly, but what this slide is really telling us is this problem, finding a Hamilton cycle, it's hard. Finding an Euler circuit, that's not too hard. This is something we can certainly do. We've got algorithms to do this in linear time. But for Hamilton cycles, that's hard. So why is that? Well, the definition is very similar. Eulerian, Hamilton. In Hamilton or Hamiltonian, vertices appear exactly once. But in Eulerian circuits and trails, we have that every edge appears exactly once. So the difference here is the word edge versus the word vertex. Although that slight change looks like these problems are really the same, or at least similar, turns out they're not. They're turned out to be quite vastly different. So in the question of finding an Eulerian circuit, there is a fast algorithm to check if a graph has an Euler circuit, where the running time is actually a linear function in the sum of the size of the vertex and edge sets. And namely, our test is it connected, and do all vertices have even degree, which are quite straightforward to check. Unfortunately, there is no fast algorithm for checking whether a graph has a Hamiltonian cycle. And in fact, it turns out the problem of deciding if a graph has a Hamiltonian path or cycle is NP complete. So this is a part of characterization of problems and their difficulty. So it is widely believed that there does not exist an algorithm which takes as input an arbitrary graph and determines if it has a Hamilton path or a cycle, where the running time is bounded by a polynomial function. This is really being about not being able to solve it with a polynomial time algorithm. So it's a hard problem. So how can we make a dent in this problem? Well, this is where we're going to attack it from 2 directions, necessary and sufficient. What are necessary conditions to have a Hamiltonian path or a Hamiltonian cycle? What are sufficient conditions to have a Hamiltonian path or a Hamiltonian cycle? That's what we're going to look at now. So just a quick review of what these terms mean. If P is a property of a graph and C are a set of conditions that a graph can satisfy, you can also think of this as P is a set of properties, C is another set of properties, then this collection C of conditions is necessary for property P to hold if every graph that satisfies P must also satisfy the condition C. We typically write this as P implies C. On the other hand, we say that C is sufficient for P if satisfying C implies that it also satisfies P. So we write that as C implies P. If C is both necessary and sufficient for P, then we say P is true if and only if C is true, and we say that C characterizes P. We also write this symbolically as P if and only if C, or P implies C and C implies P, or P is equivalent to C. Those are all sort of similar ways of basically expressing what this is. So let's look at a couple of examples. It is necessary for G to be connected to have a Hamilton path. So in this case, we are thinking about this as our condition C, and this as our condition P. And so it's saying that C is necessary for P. In other words, P implies C, or Hamilton path implies the graph is connected. So this means if the graph has a Hamilton path, it must be connected. That means that we can use this result in the following way. If the graph is not connected, it can't have a Hamilton path. So this is equivalent to not connected implies does not have a Hamilton path, where we are using this not symbol. So just borrowing some terminology and symbols from Macm 101 when you did logic. How about number 2? Being a complete graph is sufficient to have a Hamilton path. So what that means is being complete implies there's a Hamilton path. So those are examples of necessary and sufficient conditions. How about a necessary and sufficient condition? Well, we don't have one for Hamilton paths. We do have one for Euler circuits, so that's the one we're going to base this example off of. So we're going to start with the assumption that G is connected and not the singleton graph. So in other words, it doesn't consist of just an isolated vertex. In this case, there's more than one vertice. So those are just the baseline assumptions we have to make. And this is just to avoid some of the trivial examples. So we've got G is connected and not a singleton graph. Then what do we have for necessary and sufficient condition for an Euler circuit? Well, we have that if all vertices have even degree, then that is necessary and sufficient to have an Euler circuit. All right, and so that's what we would really like to have, a characterization of what it means to have a Hamilton path or a Hamilton cycle. Here we've got a characterization of having an Euler circuit. We also have one for Euler trails. It was exactly 2 vertices of odd degree. But we can't get a characterization like this for Hamilton cycles or path, and that's because of the previous slide and the problem being an NP complete problem. So what's the best we can do? The best we can hope for is to have a collection of necessary conditions and a collection of sufficient conditions. So that's where we're going to focus our attention. We'll focus our attention on a couple of necessary conditions of having a Hamilton path, and then we'll look at a sufficient condition for having a Hamilton path. So what's a necessary condition? Well, here we have that if G has a Hamilton cycle, then G take away V is connected for every vertex in V. So if I remove any vertex from G, the graph remains connected. So here we would write this as Hamilton cycle implies G take away V is connected. I'm being very brief here, but I just want to get in your mind the implication that's happening in this theorem. Hamilton cycle is the hypothesis. G take away V being connected is the conclusion, and that's true for all vertices V. So how do we prove this? Well, we've got that G has a Hamilton cycle. Let's call it something. We'll call it C. So C is a cycle that contains every vertex in the graph G. for any vertex, C take away V is a path through all vertices in V take away that vertex. And that's all the vertices of G remove V. So G take away V is connected because we have a path that passes through all the vertices of it. And we are done. So how do we use this result? So this says if it has a Hamilton cycle, then G take away V is connected for every vertex. So how can we use this? We'll do an example here. Example. Consider this graph. The bow tie graph. So this bow tie graph kind of looks like a bow tie, two triangles stuck together. Let's focus on this vertex here in yellow. I'll call it V. Well, G take away V is disconnected. Because I remove that middle vertex, I basically get just two vertices on one side with an edge connected them, and then the two vertices on the other side with the edge connecting them. So if I remove V, I get a disconnected graph. That means the original graph can't have a Hamilton cycle. Because if it did have a Hamilton cycle, then removing any vertex from the graph wouldn't disconnect it. But this one does disconnect it. So G does not have a Hamilton cycle. So that's an example of how we can use that theorem. How about the next necessary condition? This one says if a bipartite graph has a Hamilton cycle, then the size of the two vertex sets in the bipartition have to be the same. Why is this the case? We can get a picture first. Sometimes it helps to think in terms of a picture. So we've got our bipartite graph. We've got our vertices in one half of the bipartition. We got our vertices in the other half. And this graph has a Hamilton cycle. So what that means is there's a way to arrange the vertices in each half of the bipartition in such a way that our cycle looks like this. It goes across and then back, and then across and then back, and so on. Across and then back, across, and it's got to come back again. And I can't come back to a new vertex without having another partner to go over to the right to, because I've got to be on a cycle. So eventually, it's just got to come back around and connect back to where it started. And if I think about then what do the number of vertices on one side have to be compared to the number of vertices on the other side? Well, they have to be equal because there always has to be a matching pair. So what we have is that a Hamilton cycle has the form V1 and then a partner in the other half of the bipartition, W1, and then come back to a vertex V2 and then W2. So I can label them here, V1, W1, V2, W2, all the way down to some VK across to some WK. So VK to WK, and then WK has to come back home to V1. So they have to occur in pairs. And so on. So because they occur in pairs, and every vertex appears here, with V1 appearing twice, because it's a cycle, so I had to come back and close in on it. But every vertex has to appear, and they had to occur in pairs. And so that means the size of V1 is equal to the size of V2. They both are equal to K in this case. And so there we go. So how could we use this theorem? Well, as an example, K2, 3, the complete bipartite graph with two vertices on one side and three on the other does not have a Hamilton cycle. And that's because If it did have a Hamilton cycle, then the two sizes of the vertex set would have to be the same, but in this case they aren't. One's of size 2 and one's of size 3. So that's again how we can use this result. Now that brings us to a sufficient condition to have a Hamilton path. So what this theorem says is that if G is a graph with n vertices, and we have a condition on the sum of the degrees of any two vertices, it's big enough. That's all this is really saying, is that for any two vertices, the degree of one plus the degree of the other is large enough. It's bigger than or equal to n minus 1. And that's for all pairs of vertices that aren't equal to each other. So we're looking at all distinct pairs of vertices. If that's the case, then G has a Hamilton path. So let's have a look at how to prove this. Now this is going to be quite a long proof. You can see in the space that I've left in the notes, I've left a lot of space to fill in the details, but we will break it down into bite-sized pieces. So we'll start with first calling this assumption that we have, this hypothesis on our graph, calling it star. And so what can we conclude from star? Well, we start by showing that star implies G is connected. So we start by showing that star implies that the graph is connected. So we'll make that our first claim. So we'll call this claim. And we'll say, what is our claim? By star, G is connected. And let's prove that. So in order to prove this, we'll use a proof by contradiction. So we'll go towards a contradiction. Suppose G is not connected. So if G is not connected, then it has at least two components. So we'll let V1 and V2 be vertices in different components. Say capital H1 and capital H2. So those are our two components. Let's let N1 be the number of vertices. So that'll be V of H1. That's just denoting the number of vertices in the graph H1. And we'll let N2 be the number of vertices in the graph H2. Then we have that N1 plus N2. That's the number of vertices in one component plus the number of vertices in another component. There may be more components, who knows? But the idea then is that this is less than or equal to n, the number of vertices in the graph in total. Okay, so now what do we have? We know that the degree of V1 plus the degree of V2 by star, it is greater than or equal to n minus 1. That's by star. But remember, there's two components at least, and V1 is in one component and V2 is in another component. Degree of V1 plus degree of V2. Well, V1 is in a graph, a subgraph, with exactly n1 vertices. And these are graphs, these aren't multigraphs. So because V1 is in a subgraph with exactly n1 vertices, I know its degree can be at most n1 minus 1. Again, let me reiterate what we're using here. V1, it's in a component with n1 vertices. So best case scenario in terms of its degree, what's the biggest degree it could have? Well, that vertex could get connected to every other vertex in the component it lives in. That means it's connected to all n1 minus 1 other vertices in its component. So that's its degree. It's at most n1 minus 1. Similarly, for the degree of V2, it could be connected to all the other vertices in its component, which means it has degree at most n2 minus 1. But that is n1 plus n2, that's n, minus 1, that's minus 2. So this tells us that the sum of the degrees is less than or equal to n minus 2, but that contradicts assumption star, which says that the degree has to be bigger than or equal to n minus 1. And so what we have here is that this contradicts star. So something went wrong. What went wrong? Well, it was our assumption. Towards a contradiction, suppose G is not connected. If it's not connected, we get something that's impossible that happens. So therefore, it had to be connected. So therefore, G is connected. Okay, so I'll put a little bar down here indicating that we started off our proof by showing some smaller result which is going to be useful for us. So we now know that G is connected. Now we're going to show that it has a Hamilton path. So how are we going to do this? Well, we're going to start with a path of maximum length in G. So consider a path of maximum length. Well, we'll call this path P, and it's going to look like this. It's going to start at V1, go to some vertex V2, then V3, and so on, all the way up to vertex Vm. So there's our path of maximum length in G. If all the vertices of G live on this path, then we're done, because by definition that is a Hamilton path. So we have two cases to consider. So case 1 is P contains all vertices in G. Then we are done. P is a Hamilton path. So that brings us to case 2. Otherwise, P does not contain at least one vertex from G. There's some vertex in G that's just not on P. I've changed the color to red here, and that's because we're going to show that this case actually can't happen. That's what we're going to do below. We'll show this case doesn't happen. And by doing that, it means that, well, there was really only one case we have, and that was that the path of maximal length did contain all the vertices in the graph and therefore was a Hamilton path. But right now we're stuck in this otherwise case, where the path does not contain all vertices from G. This means our graph had n vertices, our maximal path had m vertices as I've listed there. So this means that m is strictly less than n. our path contains less than n vertices on it. So what can we do with this? Well, I'm going to come up with another claim. This is just breaking these things down into smaller bite-sized chunks so we can get a handle on it. So what's our claim? Our claim is by star, there is a cycle containing those vertices on that path P. So there must be a cycle containing those vertices. Let's prove that. Let's prove this claim. Well, since P is maximal, we can't extend it any further to a longer path, then V1 and Vm, so the starting vertex and the ending vertex for that path, are adjacent only to vertices on the path. So what this means, if we look back up at our path picture, is that any edge that's coming off of V1, well, it's got to connect back to some vertex on this path. Anything that's coming off vertex Vm has to connect back to vertices on this path. We can't have this connecting to some other vertex because that means we couldn't extend the path. We can't have this one connecting off to another vertex because otherwise we could extend the path and therefore it wouldn't have been one of maximum length. So what that means is that we basically have, again, a couple of cases. If edge V1, Vm is in the graph G, then we are done. We have found that cycle containing the vertices. That's what I'm trying to prove. There's a cycle containing those vertices. So then we're done because we have V1 connects to V2 connects to, and so on. We've got our underlying path up to Vm, and then we have this edge that makes a cycle. Well, what else could we have? Well, we could have that else if V1 is incident with Vi and Vm is incident with Vi minus 1, then we have a cycle as desired. So why is that? Well, again, we got a picture that looks like this. V1, V2, and so on. We'll label Vi minus 1, Vi, up to Vm. So this is saying we have V1 is connecting to some Vi, and then Vi minus 1 connects to Vm. And so that gives us a cycle because we could just delete the edge between Vi and Vi minus 1, and we see our cycle now. Goes around, comes back, and goes around. So there we get our cycle through our vertices. So that's another case we could have. The final case is else V1 is incident with k vertices on that path. We know that the neighbors of V1 are living on that path. Then Vm is incident with m minus 1 minus k vertices. Why is that? Well, let's think about the previous case. V1 is adjacent to Vi. In this last case, we are assuming then that Vm is not adjacent to the one prior to it. So of all of the ones that V1 one is adjacent to, so it's adjacent to, we were thinking of k of them here, then the ones prior to it, it's Vm is not adjacent to. So Vm is not adjacent to that one, that one, that one. No, that was adjacent there. So it's not adjacent to that one. So how many is it not adjacent to? In this case, our degree of our V1 as shown in the picture, the number of neighbors it's adjacent to is 1, 2, 3, 4, where the little circles are drawn. And so Vm can't be adjacent to those four x's, which are to the left of the little circles. So it can't be adjacent to k vertices. If V1 is adjacent to k vertices, then there are k vertices that Vm can't be adjacent to. So of all of the vertices it can be adjacent to, m minus one of them, that's how many is in this list that it can be adjacent to, we had to remove k of them that it's not allowed to be. And so that's how many are left for it to be adjacent to, m minus 1 minus k. So then we have that the degree of V1 plus the degree of Vm is k. M1 is incident with, at most, I should have said at most. We'll move that over and say at most, because it doesn't have to be incident with them. It's just incident with at most this many. So the degree is less than or equal to k plus m minus 1 minus k. And so the sum of the degrees is at most m minus 1. But here, we are assuming that m is less than n. We are assuming the number of vertices on our path was less than the number of vertices in the entire graph. And so this is less than n minus 1. And that is a contradiction to star. So this contradicts star. Let's remember, if we scroll up, what is star? Star is the assumption we have. It says that the sum of the degrees has to be bigger than or equal to n minus 1 for all pairs of vertices. And here we've found two vertices for which the sum of the degrees is strictly less than n minus 1. So what does that mean? It means that this case can't happen. If this case happens, we got our cycle. And if this case happens, we have our cycle. So we are done. We have just proven that by star, there is a cycle containing V1 through Vm. And it falls into one of those two cases. So we can close off our proof of this claim. And we'll block it off. And so now let's backtrack to see where we are. We constructed a path of maximum length, and we are trying to show that it actually contains all the vertices. So if it doesn't, we are in this case here. And we have just shown that there must be a cycle then. In this case, there must be a cycle containing those vertices. So not only is there a path with V1 through Vm, there in fact is a cycle on the vertices V1 through Vm. So that's what we have. So we'll jot that down. So let C be the cycle on V1 to Vm. And it doesn't say it has to appear in the order that they appear here. So we will just draw out a cycle. We got a Vi, a Vj, a Vk, and so on. I'm not even going to put subscripts for the rest. I'm not really interested in those. It's just all the V's appear in some order here, and there's our cycle. So that's where we're at so far. And not all the vertices in our graph appear on this cycle. So there must be another vertex somewhere. So let's call it W. So let W be another vertex in G, not on the path P. So it's not one of these vertices V1 through Vm. Again, we are in this case, so I'm writing in red here because we are still in this case of otherwise. P does not contain at least one vertex from G. And we've shown that in this case, we've got that there must be a cycle. We've proven that, so there we've drawn out our cycle. Now we'll let W be a vertex that's not on that cycle. And so there must be an edge that connects to it. In fact, it could have a few vertices on it, but the point is there must be at least one edge. To travel along in order to get out to that vertex W. So what does that mean? Well, that's perfect now because there's at least one edge there. Then look what we can do. We can go along that, which is at least one edge, and then around the cycle. And I'm going to stop here. Why have I stopped there? Well, because now I've produced a path that is longer than the maximal path that I started with. So then we can produce a path, and I'll call that path Q in this case, which I've drawn in here, which has a length. What's its length? Well, its length is, we have m vertices going around. It's on all those m vertices. So it's passing through all those m vertices. So it had length m minus 1, and then plus whatever edge is on that green section, and that's at least 1. So this has a length at least m, which is longer than p. And that's a contradiction because P was supposed to be of maximal length. And this is a contradiction. And so that means, let's back up where we were. So we have just said otherwise. Suppose P does not contain all the vertices in the graph G. Then there's at least one that's not on it. So if this maximal length path does not contain all the vertices, then we are trapped in this case 2, which I said we will show that this case can happen. So we are in case 2. We have just established that there must be a cycle on those same vertices. But if there's a cycle on those vertices and there's a vertex that's not on them, then we can always produce a longer path. And that's a contradiction. So this contradiction means we can't be in case 2. So case 2 cannot happen. And therefore, if case 2 cannot happen, then we can only be in case 1. And case 1 was, well, our maximum path already contained all the vertices, and therefore it was a Hamilton path, and therefore we have a Hamilton path. So therefore, we must be in case 1. So there is a Hamilton path. And that's the end of our proof. And that's a long proof. I said the Euler circuit proof was probably arguably our longest one. This one rivals it in terms of length. So they are both quite long proofs. But we've now got our result established. And our result is that as long as the degrees of the vertices are large enough, in fact, this is really a condition on the pairs of vertices having high enough degree, then we're going to get a Hamilton path. What can we get from this then? Well, as a corollary, we can get that if every vertex has degree at least n minus 1 over 2, then we have a Hamilton path. And the proof of that is for any VW in the vertex set, the degree of V plus the degree of W is at least n minus 1 over 2 plus n minus 1 over 2, which is at least n minus 1. And so that implies there is a Hamilton path by the previous theorem. And so this is a nice result that says if the degree of every vertex is big enough, then there must be a Hamilton path. We'll end with this statement here that says the corollary is tight in a certain sense. What this means is that if I drop this number at all, then we run the risk of the result not being true, in that there is a counterexample. So here, I'm just going to drop that number by a half. In other words, if we make it so that the degree of every vertex is at least n minus 2 over 2, then the result doesn't hold. We can have graphs where the degree of the vertices is quite big, it's greater than or equal to n minus 2 over 2, but it still doesn't have a Hamilton path. And so what would be an example of that? Well, an example would be we take a copy of k sub k, and it's going to look like this. We've got these edges. So complete graph on k vertices. And so it looks like that. And I just take a second copy of that same thing. And let's let that be our graph G. Then n is equal to 2 times little k. And what is the degree of any vertex? Well, the degree of any vertex is little k minus 1. And so that is n over 2 minus 1, or in other words, n minus 2 over 2. So we are in a situation where every vertex has degree n minus 2 over 2. But there is no Hamilton path in this graph. Why not? Because it's disconnected. So G is not connected. So does not have a Hamilton path. So this is an example where we got vertices that have quite large degree, just not large enough in order to guarantee a Hamilton path. Just not large enough. They're just a little too low, by a half in each case. All right. Well, that's it for this section. Thanks very much for watching, and we'll see you again next time.